composite Simpson's rule. These both require the use of the midpoint of the interval. So because we must use a midpoint of the interval, we have to divide into an even number of subintervals, and then we can pair two intervals together. If I have my interval from A to B, so we have 1, 2, 3, 4, 5, 6 subintervals here. We're going to have to apply it on pairs of intervals. So for example, this first one requires us to have a parabola that goes through these 3 points, and that's like the top of our of our rectangle. I know it's no longer a rectangle, but so we'll have our parabola, and people always make the mistake, and I do it too, of trying to like always put the vertex at the midpoint, but we don't necessarily have to have like the, top or the bottom of the parabola at the midpoint. I guess this could go like that maybe. That is a terrible parabola. It's okay. My intervals are all equal. I got something accomplished in this picture. So maybe these are like rectangles. Those are all supposed to be pieces of parabolas. I'm terrible at drawing, so yeah, just, you have to believe me. So anyway, n equals 6 subintervals. We apply the method n over 2 times on pairs of intervals. Because to uniquely define a parabola, we need pairs of intervals. Let's go ahead and estimate the integral from 0 to 4 of e to the x dx. We're going to assume that n is 4 here. So if n is 4, we also have h, and h is the length of our intervals, and it's always calculated by b minus a over n. So b minus a is 4, n is 4, so h, which is the length of our subintervals, is 1. So what composite Simpson's rule looks like is, remember, it's the integral from a to b, f of x dx equals, we have h over 3 times f of a plus 2 times the sum from j equals 1 to n over 2 minus 1, f of x 2j plus the sum from j equals, oh, sorry, that's 4 times the sum, because these are the midpoints, which, if you recall regular Simpson's rule, they do get, the midpoints get multiplied by 4. 4 over n over 2, or 4, j equals 1 to n over 2 of f of x 2j minus 1 plus f of b. So this is composite Simpson's rule. It looks really messy, but realistically, what you need to remember is to figure out f of a, figure out f of b, and then with the remaining nodes, you're doing 2 times the sum of all the nodes with even subscripts, so that's the 2j, and then you're doing 4 times the sum of all the other nodes with odd subscripts. So instead of, trying to sort out this weird formula, you can just remember it that way as well. And so I will write out what my, I spilled water on my iPad. That's why my screen is getting to spaz out while I wipe it off. Okay, so I do find it's helpful for something like this to just write out what the interval is. So if we're doing the integral from 0 to 4 e to the x dx, that's equal to, again, h over 3, and h was 1, times e to the 0, that's f of a, plus, and then we have 2 times the sum of f at all of the even subscripts, not including the first and the last one. So that's really just x2 in this case. So e to the x2, which is 2. Then plus 4 times, and then we sum the values of the function at the odd subscripted numbers, which are, or nodes, which are x1 and x3. So 4 times e to the 1 plus e cubed, and then plus f of b, which is e to the 4th. This is what, composite Simpson's rule gives us. And then if we plug this in to Wolfram alpha or the likes, we end up with 53.864. So that's our estimate. And then integral from 0 to 4 of e to the x dx is actually equal to 53.598. Part of the reason I chose this example is because, like, e to the x it's not a nice function. It's not something that just, like, behaves relatively nicely. Like, it grows pretty rapidly. And yet, even though we're only using information at 4 or 5 different nodes, we're getting a very accurate estimate, given the fact that e to the x does have so much, slope, and such rapidly changing slope, and the fact that we have intervals of length 1, which aren't even that small. So this is really nice. Obviously, there's the flip side where this is a dumb example in the sense that we know that the integral is, e to the x. So if we calculated definite integral, we would get e to the 4 minus e to the 0, which is way less calculations than actually doing out Simpson's rule. But I wanted to demonstrate, not this, but demonstrate that these match quite well. Although this particular example is a little dumb in the sense that, we're doing too much work. There are, I want to remind you, like I said at the beginning, there are functions that just aren't integrable. Things like e to the x squared even. We don't have a function that describes the integral of this function itself. So we do need to use estimation methods, and something like Wolfram alpha will use estimation methods if I asked it to find the integral from 0 to 4 of e to the x squared.